Now, having introduced the concept, the notation of J, the total angular momentum, and the J ladder operators, the J plus, the raising operator, and the J minus, the lowering operator, in a bit more detail, spelt out here. This is the quantum mechanics that we want. We want the J to have these sort of properties, and then we can use these later and make deductions about what these little J's stand for and so forth. So this is a kind of target. This is what we want the quantum mechanics of the total angular momentum. When you have a J as a sum of two angular momenta, J equals J1 plus J2, and then when you make those operators, J hat equals J1 hat plus J2 hat. We want that J hat and its corresponding, like the Z component of J. We want it to have this kind of property, and we want that raising and lowering, the so-called ladder operators, to have this property. Now with all this is just, instead of J, just put L or S. Things are much simpler in the S case because there are only two eigenstates, there are only two allowed eigenvalues, right, up or down for spin. But well, think L, and then you'd have L here, and L, and so on. So we'd like the total angular momentum to behave in much the same way as the L, the orbital angular momentum case. And why is that? Well, it seems reasonable, and as always, you never know until you try. Right? So much of quantum mechanics is you're just guessing when you start. Like, how do you know what the appropriate operator is? Well, see, we don't. I mean, this is a new operator. It's an operator. This J squared and JZ, they are two new, well, these as well. You've got, well, I've got four new operators, the raising and lowering J hat also. So we've got four new operators here, and we're just sort of, well, guessing is a bit too strong, but we don't really know what the appropriate operators for a total angular momentum should be. What should the, well, we suspect it'll be something like it. We'd like it to be something like this because it's analogous to the L case. We just have one angular momentum. So okay, so that's sort of in a sense our goal, right? Now I think, where is it? I think it's a bit later in a session to follow. Well, actually, I think I asked you to do it as homework to show that actually that J squared and JZ commute, and you show that using the well, for a particular case, I think where J is equal to well, remember J is J1 plus J2. I think J1 is an orbital angular momentum L, and J2 is a spin S, and so your J then J hat equals L hat plus S hat, and it's one of the homework exercises to show that J squared and JZ commute. Right? Now, assuming they do commute, you know from earlier theory, if two operators commute, their commutator is 0, and they share the same set of eigenfunctions. Okay? So assuming these two commute, and therefore they have the same set of eigenfunctions here. See? So this is the eigenfunction for the JZ operator, and it's the same set of eigenfunctions for J squared operator. Right? So assume that's assumed here. Actually, these two equations have quite a lot of information in it. Yes, information dense. What else do you notice? Now, J squared, that's the angular momenta. Now, that shouldn't change depending on your choice of Z. Right? That's sort of intrinsic, it's sort of just physical. Whereas when you're taking the Z component, it depends on your choice of Z. Right? So the raising operator shouldn't really change anything in terms of eigenvalues for your J squared. That seems reasonable if you think about it. Okay? Now, analogous to your L squared, where you had LL here, like here was your, well, this actually, your eigenvalues for J squared, right? Corresponding to when you had L squared, you had L here. Okay? And so the raising and lowering operators don't have any effect on your eigenvalues. They don't change anything. And that seems reasonable. But when you apply the raising and lowering operators to your eigenstates, when the operator is the projection, the Z component, or the component of the total angular momentum J along the Z axis, that's what this is. The corresponding operator. Then if you've got a raising operator J here, this J here will change this the eigenvalue of this state to make it m plus 1. Okay? And if you're using the lowering operator, the eigenvalue gets changed. It goes down by 1 in units of 1. So that's sort of our target. That's what we'd like, right? And these two simultaneous, the same set of eigenstates because J squared and JZ commute. We're assuming. All right. That's what I've just been saying. Now the equation, these sorts of equations for J are similar to those of L. We assume that J is non-negative, right? It's a total angular momentum. So greater or equal to 0, and its eigenvalues, your little j, the equivalent of little l, in this case, take on. Now we want. Now j is a sum of two eigenvalues, so two angular momenta, right? J1 plus J2. So that could be like an orbital angular momentum. So the eigenvalues there change in units, whereas the spin, the m values for spin, they change by units, but they can have half integral. So the spin can be the angular momentum spin can have half integral values, like s is a half. So if your j here is going to be like orbital angular momentum plus spin angular momentum, you want your eigenvalues for j to be half integral. So j can take on eigenvalues 0, a half, 1, 1.5, 2, ... Okay? That's what we expect. That's what we want. And then for a given j, your m of j, the projection, the component of your j along the z-axis. That's what this mj. Now before we had ml or ms. Now we've got mj. So that's the m here, mj. That's the component, the projection, if you like, of the j, the total angular momentum along the z-axis. And it too will have, so your mj ranges between minus j and j, and the j goes up by units of a half, right? No, 1. Okay. So these mj values, they range between minus j and j, step up in units. So these mj's can have 2j plus 1 possible values. Right? We had a similar story with the orbital angular momentum, L. right? The m had two L plus 1 different values. So for example, say j is 1.5, 3 over 2. So your m of j will range over minus j. So minus 3 over 2, and then you add 1. So you get minus half, and add another 1. Increments of unit 1. So minus a half plus 1 gives you plus half, and then add another 1, you get 3 over 2. So minus j plus j. So four values. Does that make sense? 2j, so it's 2 times 3 over 2, that's 3 plus 1, it's 4. 4 values, so it fits. Right? Okay. Now, swap around. So, something a bit new. I'm going to talk about two kinds of, in the context of a composite, a composite system. Anything that's composite means it's composed of something, and that means it has parts, which means it has more than one part. Okay, so a composite system is a multi-part system. So in the context, say, of addition of angular momenta, plural, you can, well, the concept of coupled and uncoupled, what does that mean? Well, the definition of these two terms, I'm just getting you, presenting the terms to you, because it'll take a couple of sessions via examples to explain what it means. It's not easily expressed. So you can express a composite system, a multi-part system, in two ways. There's the so-called uncoupled way of representing it. And what do you mean by a representation of